Hi everyone, my name is Lily. Today I'll talk about the Boyer and Moore algorithm, a pattern matching algorithm that claims to run faster as the pattern length increases. So here we look at an example problem where we are given a text and need to find a pattern. So please note that in this presentation we call the string as text and the patterns as patterns, and also let n be the length of the text and n be the length of the patterns. Please remember this, as this term will be used throughout the presentation. So in this example, the pattern should be found at index 8 of the text. So to solve the pattern matching efficiently, we have the Boyer and Moore algorithm. The algorithm is developed in 1977 by Professor Boyer and Moore. Hence why it's called Boyer and Moore algorithm. It is one of the most efficient string searching algorithms and often the benchmark for pattern searching. So the Boyer and Moore achieve high efficiency by pre-processing the patterns. We'll talk about it later in the presentation. Think of when hitting Ctrl F in a Notes or Word document, or search for a specific word in a database. You might be using Boyer and Moore's algorithm every day. It even shows up in bioinformatics field, where we need to locate exact DNA or protein motif inside huge sequences. Let's talk about the application constraint of the algorithm, where it is invalid, incorrect, or not appropriate to apply the algorithm. Think of it, when hitting Ctrl F, you can only find the exact text. You can't really ask for something like, give me all the text that related to fish. This is exactly one of the constraints of the algorithm. No typo, approximate matches, or wildcats allowed. The algorithm also works on decoded text only. Encrypted or compressed data must be decoded first. And for the edge case, if the pattern is empty, you must define behaviors, and if the pattern is longer than text, no match is possible. Boyer-Moore is the combination of the two approach, bad character heuristic and good stuff heuristic. Both of these approaches involve pre-processing the patterns and build a lookup table. Just apply different rules on how to process when the character is mismatching. Both of heuristic can be used independently to search pattern in text, but for today, we only talk about one approach, that is the bad character heuristic. So the idea of bad character heuristic is very simple. Remember, the pattern matching is done backwards, and the character of the string which doesn't match with the current character of the patterns is called the bad characters. Then once start scanning the character, if there's no match, we shift the patterns until these two cases are met, where case 1, mismatch become a match, and case 2, the patterns move past the mismatched character. We will see this in the next few lines. So now I will introduce you a very important step of the Boyer and Moore algorithm, which is to pre-process the pattern. We want to build a fast lookup table for the bad character rule. We're doing that by taking each character in the pattern and store its last occurrence of every possible character in an array of size equal to the alphabet size. What does that mean is we have this as the pattern. We store each possible character, which means we have A, C, B, and D. We only want the last occurrence of each character, and we don't want the repetitive. So, for example, at letter C, the last occurrence of letter C is at index 2 and not index 1. Why are we doing this? Pre-processing creates a simple mapping table that tells us how far to shift the pattern on the mismatch, making Boyer more fast in practice. We will discover more on the next slide. So let's talk about case 1, where mismatch become a match. In theory, when mismatch become a match, we shift the pattern so that the next character in the text align with the last occurrence of it in the patterns. What does that mean in practice? Here we have a mismatched character. Here is A, the bad character. We got A at the position 0 in the patterns, and also A, the last occurrence of A in the pattern is also 0. Now we shift the pattern 2 times so that A in the pattern get aligned with A in text. Let's look at case 2, where the patterns move past the mismatched character. In theory, we will look up the position of last occurring of mismatching character in the patterns, and if the character does not exist, we will shift the pattern past the mismatched character. Here, the mismatching character here is F. This character does not exist in the patterns. Therefore, we shift the patterns past this character, which means we will shift the patterns past index 7 to index 8. We're doing this because F does not exist in the pattern, so at every shift before position 7, we will get mismatch and our search will be meaningless. Therefore, after we shift to position 8, we get a match. Let's talk about the time complexity of the algorithm. The worst case happens when all the characters of the text and patterns are the same, causing the jumps to collapse to 1, which means every time the pattern shifts, it's only shift 1 step away, causing the algorithm to recheck many characters. This can cause up to n times n time. The average case is about O(n) time. In normal text with a decent alphabet, most mismatch happen near the end of the pattern. That would trigger big jumps, so the work is about 1 pass over the text. In best case scenario, when the pattern's characters are very rare or very distinctive, each mismatch let us skip roughly the array size, so we only examine about n over m alignments. So let's talk about the practical limitations, things that limit performance and usability. First of all, with 2 to 3 character patterns or an alphabet, like DNA patterns, where single characters are very common, partial matches are very common too. So the shifts are small and we gain a little over the brute force approach. For adversarial input, like I talked earlier in the times complexity slide, each alignment nearly matched and then fail at the last characters. The pattern shift by just 1 each time, so the algorithm behave close to the naive case. Last but not least, because we built the table with patterns and searching lots of changing patterns can be slower overall, and there are better algorithms for that purpose. Here is a fun property of the Boyle and Moore algorithm. This algorithm often gets faster as the pattern gets longer. Now, at this point, we know that when we hit a mismatch on a character that isn't in the pattern, we can jump by about the pattern length. So for example, here we have a text of 24x, and we have an example pattern of banana is sweet, which have 13 characters. This pattern only needs to jump twice to go through the 24x, whereas a shorter patterns of high needs to jump 12 times to go through all of the x. In short, we have longer pattern, bigger jumps, fewer alignments. Thank you for watching and hope you enjoyed this presentation.